Hello my friends, and here we go for the final method implementation of this agent class. We're going to define now the method that will softly update the target network's parameters, and we're going to call this method soft update. So here we go. What is going to take as parameters? Well, first self for the object, then it's going to take our local Q network, so we can call that local model, then the target Q network, which we can call target model. I'm just taking different names here so that we don't confuse with our variables created before. And of course, it's going to take as the last argument the interpolation parameter. Perfect, here we go. So colon, and then let's implement the soft update method. So first, what it's going to do is loop through the parameters of the local Q network and the target Q network. And so we're going to start with a for loop here that will loop through first the target parameters, so I'm calling this target param to keep things simple. Then it's going to loop through also the local parameters, meaning the parameters of the local model. So I'm adding here another loop variable, which I'm going to call local param. And then the trick to get those parameters at the same time is to use the zip function, which will take as arguments, of course, well, the parameters of the target model and the parameters of the local model. And how we're going to get them? Well, first, we're going to take our target model, from which we're going to call a certain attribute, because remember, of course, target model is supposed to be here our target Q network, which we created here, target Q network. And remember, since this is created as an instance of the network class, and since the network class inherits from the module class by the NN module, well, we can use this attribute parameters, which will give us the parameters of the model. All right, so let's go back down. And that's exactly how we're going to get those parameters. So after target model dot here, I'm just going to add parameters and then some parentheses. All right, perfect. Then we're going to do the same with our local Q network, our local model. So I'm going to add a comma here and then paste it, and then just replace target here by local. All right, perfect. So let's add some colon here for the for loop, and then here we go. Let's now implement what's going to happen for each target parameter and local parameter of our two Q networks. So actually now is the time to do the soft update. And so as a reminder, the soft update consists of, well, softly update the target model parameters using the weighted average of the local and target parameters. And so first here we're going to take our target parameters, target param, and then since we want to update them, the target parameters, well, we could do an update like this, but instead we're actually going to use the copy function to update the parameters of the target Q network. And so the trick to do this is just to add here dot data and then dot copy underscore, which is actually a function. So I'm adding some parentheses here, and inside the parentheses you're going to have how you want to update those target parameters. And well, the formula of the soft update of the target parameters is as such. First, you take your interpolation parameter, which you multiply by your local parameters, local param. But actually, again, here to get them precisely, you need to add dot data. So that's the first part of the formula. And then you're going to add, well, this time 1, which I'm writing as a float, minus, again, the interpolation parameter multiplied by the target parameters, target param. And again, to exactly get those parameters, you need to add dot data here. And there you go. Double congratulations, because not only we're done implementing the soft update method, but also we're done implementing the agent class. So congratulations. We did some good work here, and mostly we have everything we need, meaning all the tools to implement the training. Now, what I'm going to do is just summarize everything we've just done here in a few words. So I'm going to zoom out a bit so that we can see everything, with a good bird's eye view. There we go. I hope it's not too small. Let me know in the comments if it's too small, and I can always update this and improve this. But there we go. Now we have a good look at the whole code we just implemented together. And so let me just summarize it again. First, we created this agent class that defines the behavior of an agent that interacts with our space environment using a deep Q network. And while it's interacting with this environment, well, the agent maintains two Q networks. First, the local Q network, and then the target Q network. The local queue network is the queue network that will select the actions, and the target queue network is the queue network that will calculate the target queue values that will be used in the training of the local queue network. So it's very important to understand both what they do separately, and also what's important to understand is how they interact with each other, meaning that this double queue network setup will stabilize the learning process that we implemented here. And at the same time, we have the soft update method that will update the target queue network parameters by blending them with those of the local queue network, with that formula we implemented here. And what's the purpose of that? Well, that's to prevent abrupt changes which could destabilize the training. And also, we implemented the ACT method that will help the agent choose an action based on its current understanding of the optimal policy. Those actions will be returned from the local queue network that will forward propagate the state to return the action values. And then following an epsilon greedy policy, it will return the final action. And that epsilon greedy strategy is used as an exploration mechanism. The fact that sometimes we can select random actions allows the agent to explore some more actions which could potentially lead to a better result at the end. And then finally, the learn method uses experiences that are sampled from the replay memory in order to update the local queue network's queue values towards the target queue values. Alright, and that's it. That's the bird's eye view of what we just implemented. Huge congratulations again. Now we're going to move on finally to the rest of this training implementation. We're first going to initialize the DQN agent, and then finally we will train it to accomplish a beautiful landing on the moon. I can't wait to implement those new steps with you, and until then, enjoy AI. Hello my friends, and welcome to this new tutorial. It's going to be a very simple one because it will just take one line of code to initialize the DQN agent. Because indeed, now that we're done building our agent class, well, we can finally create an instance of that class. By the way, I forgot to run this cell in the previous tutorial, so I'm doing it super quickly here. All good. We're good with our agent class, and so now we're gonna initialize the DQN agent by simply creating an instance of that class. So here we go. Let's insert a new code cell here, and well, we're gonna call our agent object very simply agent. Okay? And then, well, this object will be created as an instance of the agent class. Make sure not to forget the capital A, which will take as input, of course, the state size, but then be careful not to input action size. That was the name of the argument in the agent class, but actually when we initialize our variables just a bit above, well, we called action size number actions, or maybe you called it action size if you're used to it, but maybe number action speaks better for itself. So we're gonna take that name here, the name of that variable we initialized while setting up the environment, and we're gonna paste it right here. And there we go. That's all we need to do to initialize the DQN agent. So now we can simply run that cell, and congratulations, you now have for real an artificial intelligence. You know, all we've been doing before was just the architecture of it, you know, modeling it, but now we really have it because we finally created the object. So that's super exciting. Now in the next tutorial, we will of course train it, because so far we only built an AI with a non-trained brain, and so we need to train that brain with the tools that we implemented here. By tools, I mean the step method, the act method, the learn method, of course, the soft update method. So we will use all these tools to train the brain of our AI, and that's exactly what we'll do in this new step, training the DQN agent. So I can't wait to do this with you, and until then, enjoy AI. Alright my friends, here we go. Let's start the training implementation. So we're going to add a new code cell here, and before we start this big for loop that will perform the training, well, of course, we need to initialize the training parameters. And which are they? Well, first, it's going to be the number of episodes, which is actually the maximum number of episodes over which we want to train our agent, but you will see that it will already get some amazing performances before that maximum number, and so we'll initialize this number to 2000, okay? But you will see if we're getting the same results as when I tested it myself, well, we should get some good reward even from a couple hundred episodes. But I don't want to tell you more now. I want to keep you surprised at the end. So here we go. Let's proceed with the next training parameter. So the next training parameter is going to be the maximum number of time steps per episode, meaning that we don't want to let our AI try too hard. For example, if it keeps staying in the air, or if it stays too long in a certain stuck state of the environment, we don't want this to happen. So we're going to set a maximum number of time steps per episode. And to make things super clear here, so you can read the code easily, I'm going to name this variable, and this is just for educational purposes. I'm going to name it maximum number time steps per episode. Of course, feel free to choose a simpler variable name, but at least we will be able to read our code exactly like we would read our native language. Okay, so maximum number time steps per episode, and we're going to initialize that to 1000. In any attempt on landing on the moon, there's going to be maximum 1000 time steps. Perfect. Then, next training hyperparameter to initialize, well, it's actually going to be a series of 4 corresponding to the same thing, which are the hyperparameters related to our epsilon greedy action selection policy. Because you might have wondered, what will be this epsilon value over which we want to compare this random number generated, to either select the action with the maximum Q value or select a random action for exploration. Well, here's how we're going to do it. We're going to start with an epsilon starting value. Again, I'm taking very simple variable names so that we all understand what's happening. So epsilon starting value, which will be, of course, 1.0. All right, and that will be our first epsilon value in the epsilon greedy strategy. But then we're going to let it decay, thanks to an epsilon decay value, meaning that we're going to reduce it little by little to test other epsilon values. All right, but we're going to do that up to a certain point, and that's why then the next hyperparameter variable I'm going to initialize here is going to be the epsilon, this time ending value, which will be the last epsilon value we want to test in our epsilon greedy strategy. And this value is actually going to be 0.01. Okay, so we start at 1, we end up at 0.01, and then by which decrement we're going to go from 1.0 to 0.01, well, that's going to be with, this time, the epsilon decay value, which according to you is going to be something like what? Well, we actually want to decay our epsilon starting value and then our next epsilon values by very little, by multiplying it by very close to 1 float, and that number is going to be 0.995. All right, so for example, the epsilon starting value is going to be 1, and then the next epsilon value after the first decay is going to be 1 multiplied by 0.995, meaning 0.995, okay? And then it's going to be 0.995 times 0.995, which is a little bit lower than 0.995. And we will do that until we reach 0.01, okay? So that will allow us to get different exploration in the epsilon greedy strategy. And then, final thing, what do we have to do? Well, of course, we have to create and initialize our epsilon variable, right? Because this is just a starting value, this is the ending value, so these are fixed, this is decay value, but then we want to have the epsilon value that will vary over the different decays. And so, how are we going to initialize this epsilon variable, of course? Well, with, of course, the epsilon starting value, which I copied before. All right? Perfect. And now we have one final training hyperparameter that we need to initialize, which are going to be the window of scores on 100 episodes. Okay, so again, in order to make things super clear, I'm going to call this variable scores on 100 episodes, which will contain that window of all the scores on the last 100 episodes. And how we're going to get that, how we're going to initialize this? Well, with a double-ended queue, in order to keep track, of the scores of the last 100 episodes. And how can we get that double-ended queue? Well, that's with a certain function called the decay function, inside which we will only enter this argument, maxlen, which will correspond, of course, to the 100 episodes. And that's it, my friends. We are now ready with the whole initialization of the training hyperparameters. So now we can finally move on to that next big step, very important step, the step where we finally make our AI intelligent. But of course, having the specific intelligence, not the general intelligence, to be able to land properly on the moon. So let's make that full loop happen in the next tutorial, and until then, enjoy AI. Hello my friends, and here we go. Are you ready to implement that final training loop? I'm super ready and I'm super excited. Here we go. So we're going to start, of course, with for Then, according to you, what is going to be the loop variable? Well, that's of course going to be the episode. So let's call it episode. And our episodes are going to go in the range from the first episode of index 1 up to the number of episodes. Number episodes variable. But remember, the upper bound of a range in Python is excluded. So we have to add here a +1. All right. And here we go. Now let's implement that for loop. All right. So now, according to you, what is going to be our first step? Well, as always in a training loop, especially in reinforcement learning, the first step is to reset the environment to its initial state at the beginning of every episode. And right now, since we're dealing with one episode specifically, starting with the first episode, well, we have to reset the environment to its initial state. So how are we going to do this? Well, we're going to take our state, which here is a new local variable, and then add a comma followed by an underscore, because then we will call, of course, our environment, and then the reset function. And actually this returns not only the initial state, but also some other information, like for example, the initial observation, which is discarded here with this underscore. Okay, perfect. So then the next step, let me scroll down a bit. Here we go. The next step will be to, of course, initialize the score, because the most important thing we'll have to measure here is the score. When I say the score, it's of course the cumulative reward, which is why we have to initialize this to 0. So let's do this. We're going to call that score, obviously, and we're going to initialize that to 0. All right. So this over the episode will be the cumulative reward. Perfect. Then we're going to start a new for loop now. And according to you, what will it be iterating over? Well, of course, I'm sure you guessed it. It's going to be a loop over the time steps, right? The time steps over the episode. Okay, so we're going to start this new for loop. Then let's call our time steps t, very simply. And then, well, these time steps are going to be in the range from 0, but we don't have to specify it. So let's just specify the upper bound, which is, of course, we initialized it before, the maximum number of time steps per episode. Right now that we called it like that, it seems super easy to understand, right? So let's paste it here, and that's our second for loop. So here we go. Let's implement it. According to you, what is the first thing we should do in this second for loop? Well, actually the question should be, what is the first thing that the agent should do at a specific time step? You know, at the beginning of this new for loop, looping over the time steps. Well, of course, it will be to select an action, okay? And so we're going to introduce a new local variable, which will be the action selected. And how will the agent select that action? Well, of course, that's with one of the tools we implemented before. First, we're going to call our agent, which we just created before, as an instance of our agent class. And then, well, speaking of the agent class, we can now use one of its tools, which will be, of course, here, the act method. The act method, which, remember, selects an action in a given state of the environment and following an epsilon greedy policy. Okay? So, speaking of state and epsilon greedy, well, what are the arguments here? Of course, the state. So let's implement it now. That's, of course, the state here we got in the first step. And then, of course, it's going to be epsilon. Okay? Great. So now we have the action. So now, according to you, now that we have the action, what is the natural next step? Well, since we have the action, what does it mean? That means that the AI just played an action, it just made a move, and therefore, by making this move, it ends up in a new state of the environment. And therefore, because it played this action, we now have the next state. And of course, what do we also have? Well, we have the reward. Because each time the AI plays an action, it receives a certain reward, which, by the way, my apologies, I forgot to show to you in details. Let's have a look at what exactly this reward is. So I'm going back to the Lunar Lander environment, scrolling down to the description here. And so let's just see quickly how the rewards work. Well, after every step, a reward is granted, of course. But then, this is what we're interested in. Here is the reward for each step, meaning for each time step now in our for loop. Well, the reward is increased, decreased, the closer or further the lander is to the landing pad. Okay, makes sense. Then it is increased, decreased, the slower, faster the lander is moving. Okay. It is decreased the more the lander is tilted, angled, not horizontal. It is increased by 10 points for each leg that is in contact with the ground, decreased by 0.03 points each frame a side engine is firing, and decreased by 0.3 points each frame the main engine is firing. And then finally, we have the worst punishment and the ultimate reward. We have an additional reward of minus 100 points if the AI crashes, of course, and plus 100 points if it lands safely. And I can assure you that we will get those plus 100 points. Alright, so let's go back to our implementation. It was good to understand how the rewards work. And now, well, since we played this action and therefore reached the next state and got the reward, well, we're going to put those new information in new variables. So here we go, next state, then reward, and then also we'll also have done. The boolean saying whether we are done or not with that specific episode of the environment. And actually now, since we're about to use the step function from our environment, this will also return some other information but which we won't need, so we will just discard this information with a first underscore here and another one. Alright, and so all this will be returned by the step function of the environment, so I'm calling the environment first, and then this step function will take as argument, of course, the action. Okay? Great. And now, finally, time for the most important step of this training loop. Now is the time we're going to use the step method that, remember, includes the learn method. In other words, we're going to use the tool that will perform the training. Indeed, we have everything we need to call this step method, right? We implemented it in the agent class. Remember this step method. It needs the state, the action, the reward, the next state, and done. And well, this is exactly what we just gathered. And remember, the step method includes the learn method, which of course performs the training by backpropagating the loss between the expected Q values and the target Q values with our optimizer here and on the sampled experiences. So let's do this. That's the most important step of this training loop. Here we go. Let's use the step method to perform that new step of the training. Alright, so how we're going to do that? We're going to, of course, take our agent, from which we're going to call the step method, and there we go. We're just going to enter its inputs that we just gathered, the state first, then the action, then the reward, then the next state, and finally done. And that's it. This step is exactly what will train our agent to land better and better on the moon. Okay, perfect. So then, what is going to be the next step? Well, now that we've reached the next state, we need to update our state variable because it becomes the next state. So we're going to do that simply with a state equals next state. There we go. Then we're going to have to update the score, of course, because we got the new reward. So since the score is the cumulative reward, well, we just need to increment the score with that new reward. Perfect. And then finally, we took care of the action, we took care of the next state, we took care of the state, and we took care of the score. What is missing now? We need to take care of this. Done. And how we're going to do that? We're just going to check if at this specific time step where we are in the second for loop, well, our episode is done. And so, if done, meaning if the episode is done at this specific time step, well, we'll simply do a break so that we can finish the episode. Okay, great. And so, well, if the episode is not done, we will continue this second for loop. And if it is done, well, we will, of course, exit this second for loop. And so then what happens now? You know, when the episode is finished, well, we're going to append the score of that finished episode to that window of the scores on 100 episodes. And so, well, we're just going to take our variable here. We're going to copy it. And outside of the second for loop, be careful, we're going to paste it and then add a dot and append, of course, the score of that last episode that was just finished. Perfect. And then finally, we're just going to, of course, decay the epsilon for the epsilon greedy policy while ensuring that it doesn't go below the ending value of 0.01. And so how can we do this efficiently? Well, we're going to take our epsilon and we're going to update it this way by taking the max of first the epsilon ending value and then, of course, the decayed epsilon, which is epsilon decay value times epsilon. And my friends, now huge congratulations because we're done with that training for loop. So now I can't wait to see you in the next tutorial where we're going to do a one final print in that same for loop to visualize the training results. It's going to be a fun and exciting tutorial. I can't wait to meet you there. And until then, enjoy AI.